Hello everyone, welcome to ISMAR 2022 tutorial entitled OpenARK, Tackling Augmented Reality Challenges via an Open Source Software Development Kit. My name is Alan Yang from the University of California at Berkeley. Before we start today's tutorial, let me introduce our contributors for this tutorial. I'm currently the Executive Director at the FHL Vive Center for Enhanced Reality at the Berkeley in the Department of ECS, and I was formerly the Chief Scientist at the Fung Institute, also at the UC Berkeley. And our second contributor for the tutorial, Dr. Mohammad Keshavarzi, he received his PhD degree from Berkeley Department of Architecture and also from the Vive Center. He was formerly a generative design software developer from the Autodesk and also was a researcher at the Facebook Reality Lab. Our third contributor, Chang, he was a lead undergraduate developer from Berkeley for the OpenARK project, and after his graduation, he's currently working at the Wall Street. Since part of our research was supported by the Vive Center, and we are going to make our slides and the video presentations available on our website, vivecenter.berkeley.edu. And then you should be able to find those files shortly after this tutorial. So now let me start the first part of the tutorial to give a general introduction of the topics we're going to talk about. So I choose the title of my talk to be The True Cost to Blur Reality and Virtuality. Understand the fundamental challenges in creating virtual 3D experience. I would always like to start my talk about AR/VR using a short motivation video from Steven Spielberg's 2018 movie called Ready Player One. I'm sure that many of you have watched this movie. It claims to be the first Hollywood feature presentation based entirely on the background of a dystopia VR world. Since this is the first, it makes a lot of our consumers today believe that a future of AR/VR and the metaverse applications will look like this.
First to the key.
First to the egg.
Term AR/VR may have become a household name today, but I think the public may be still surprised to learn that the first prototype of AR/VR was invented by Morten Heilig in 1960 and 1962 with the two groundbreaking inventions. One is called stereoscopic television apparatus for individual use, and the second one is called the Sensoroma. In these inventions, Heilig already stipulated that for personal consumption of 3D content, a wearable headset needs to be manufactured, which contains two small displays, although at that time, the invention used the old CRT tubes for the display. But after the small pictures are passed through a lens group, its field of view will be drastically increased, and its focal plane will be properly projected somewhere in front of the human eyes. Another thing that Heilig paid special attention, which you only got to experience today in the Disneyland and the Universal Studio, is the use of wind and the smell to create a sense of reality. For example, in Sensorama, when the 3D movie showed that you driving down the street of Brooklyn, you could feel the vibration of the uneven street from the chair and then the motorcycle handles. At the same time, the machine will stimulate the smell of the street of Brooklyn. In 1968, of course, Ivan Sutherland further created the first prototype of wearable AR headset, which used prism, or the so-called half mirror, to merge the images from the side displays and the images from the front physical environment. Because the optical was so heavy at that time, it needed to be hung from a hanger from the ceiling so as not to crush your nose bridge when you worn it. After 60 years, if we look at the 4 major system form factors today, many of them still bear the same virtual reality modalities from their original inventions. From the biggest to the smallest, first we have the elaborately created simulation environments. These include flight simulators from the airplane manufacturers or VR escape rooms games you could find from many major cities in the US. Many of the first-gen models from Oculus or HTC Vive are tethered to PCs, a signature feature that indicated that you have a tethered VR device is that you have a long cable running from the head mount to a stationary PC, which clearly sacrifices the modality. The experience of these first-gen consumer devices could also be horrible if you have too much mobility, whereby you may hit your TV, furniture, or even your loved ones with your fist or your 3D controllers because you couldn't see them in VR. There are endless versions of these accidents on YouTube, so therefore today I'm not going to show them. This brings us to the next form factor, all-in-one wearables. These are considered to be the holy grail of AR/VR experiences, such as HoloLens. In some industrial and military use cases, you can imagine that maintaining a user's peripheral vision is very important, regardless whether you are seeing a virtual world or a physical world from your wearable. Another advantage of all-in-one is mobility. You literally carry the entire computer system on your head. Of course, the current drawbacks of all-in-one wearables are also mainly twofold. Number one, the cost of putting all the AR/VR components on your head to wear is still very expensive. Second, the weight is also substantial. For the record, the heaviest pair of sunglasses that a human wearer can tolerate should be below the 200 grams, while the HoloLens 2 currently double that number. But almost everyone has a smartphone today. So if we want to further reduce the cost of wearable AR/VR experiences, some smartphone companies such as Apple and Google are offering a set of AR library such as the AR Kit or AR Core to enable mobile AR experience directly on their smartphones. Today, when we compare the 4 form factors, we may compare based on these metrics: cost, visual fidelity, motion tracking, and the user input. For the first 2 form factors, if the cost is not a concern, today's technology can already create highly vivid AR/VR experiences. If you don't believe it, just go to Disneyland this weekend. But for our research, I believe that many technology gaps still exist that hinder the adoption of the last 2 form factors. Arguably, the last 2 form factors are the ones that consumer can afford to eventually purchase. So therefore today, we will discuss these topics on perception and the UI/UX tasks for low-cost, all-in-one applications. First, many of our AR/VR users should be noticed that as soon as you don an AR/VR headset, the virtual information is beaming to your eyes from 3 interactive spaces, so to speak. User interaction with the information presented from these three spaces presents a very different set of challenges. Next, let us first separate our discussion based on the three spaces. The first space is what I call the near-eye displayed space, or the NDS. Typically, in an AR headset, NDS is used to render 2D menu or items on head-mounted displays. For example, Google Glass with a single see-around display setting only has the NDS and does not have the other two spaces we will mention later. Content displayed on NDS typically is not anchored with any physical objects, and the triggering interaction with this content only has limited interaction methods. For example, with eye tracking, with the voice, or with 2D touch on the device to navigate through up, down, left, or right motions, like controlling a game controller. Finally, NDS is often reserved for displaying private information. Therefore, the content is rarely shared between different users on their NDS space. Next, within an arm's reach, we have the egocentric user space, or the EUS. As its name suggests, EUS is an immersive virtual space with its origin anchored from the user's own perspective, and typically will move with the user's movement. Think of this as a 3D version of a Zoom call you can hold to carry on your laptop. Typically, user interaction in the EUS is projected within an arm's reach from users, say, 1 to 2 meters away. Within this distance, as the image on the left-hand side shows, the most obvious input method are hand gestures and the 3D controller. Content on the EUS is typically not shared, unless you borrow from the example of a Zoom call, where you can deliberately hit the share button to let other people see your share screen. Even in this case, the content could be shared. Each user usually sees only an individual version of the shared data. Otherwise, think about the counter example that instead of you seeing your hand grabbing a virtual shopping cart or virtual object in front of you, a third person could extend a virtual hand to manipulate virtual objects in front of you. That could be a quite scary movie experience. The best place to create a shared working space or shared playground is in the overlaid world space, or the OWS. For this purpose, OWS models and coincides with the physical world. Many AR systems must be able to model and keep track of the physical world, such as HoloLens or the ARKit. More importantly, interacting with the OWS content implies interacting with the real world, such as the example shown on the left. If a family of 3 or 4 are playing a virtual board game on a table, then each user must interact with the virtual content at the same time that they interact with the physical table and the physical space around the table. And the origin of OWS is usually anchored at a fixed 3D location. Typically does not change also with respect to users' movement around the anchor. Therefore, in multi-user applications, an OWS and its content can be shared and manipulated by multiple users. For example, on the left, having multiple users to reach out to play the same game together will be a very natural and pleasant user experience. To summarize the pros and cons of the 3 interactive spaces, for NDS, any content should be anchored on some fixed display coordinate, because literally it serves as a regular 2D display function. A user can use voice, gaze, or 2D touch to navigate, but multi-user sharing is very rare. For the EUS, its content is anchored egocentrically within an arm's reach from the user. It is convenient to interact with the content using either natural hand gesture or 3D controllers. But at this space, multi-user sharing is still very rare and not common. Finally, for the OWS, content typically is rendered based on a world coordinate origin. Interacting with the world with the OWS implies interacting with the physical objects and its environment. So therefore, multi-user sharing in this space could be a very popular option for the applications. So based on these separation of three spaces, today we will go over selected technical challenges to really bring us to the Ready Player One future AR/VR experience, namely to finally blur reality and virtuality. So the challenges we're going to talk about today, for display technologies, I would like to highlight some of the challenges to produce retina display for AR/VR experiences. For interaction technologies, I would like to highlight perception tasks for creating egocentric 3D UI. In the OWS space, we will focus on technologies that will enable seamless content sharing across multiple users and many environments, including SLAM, digital twin, contextual spatial computing, and I will touch lightly about decentralized privacy issues. First up, what is the technology cost to create retina near-eye display for mobile AR/VR? We know that retina display was coined by Apple as a marketing jargon, essentially emphasizing the fact that when display technology can depict discrete pixels more than 60 pixels per degree viewing angle, then the human eye will perceive a continuous picture instead of perceiving the so-called screen door effect of discrete pixels. Now, let's calculate. Let's assume that the first generation retina display on the iPhone 4 generation has 960 pixels on the long side. Then 960 divided by 60 ppd will be equal to 16 degrees. So our calculation tells us that a 960 resolution display could be qualified as a retina display, but only conditioned on the fact that we must see the entire screen of 960 pixels within 16 degrees. Now let's look at the situation for near-eye display. Our human eye normally perceives 160 degree FOV horizontally or 175 degrees vertically. Now compared to the previous 16 degree, you can immediately see the problem. We need a huge number of pixels to qualify to create a retina display at the 160 degree field of view. We can forego some peripheral vision and focus only on the overlapping areas between the two eyes to create stereo vision. Over here, we still have 120 degree field of view. What that means is that for a retina display to cover the stereo near eye display area, at the minimum, we need about 60 megapixels, which is equivalent to a 8K display or TV today. Remember, that calculation still only covers for one eye. For two eyes, we will need a dual 8K resolution, dual monitors. This is just the bare minimum. Think about this is the configuration corresponding to the first generation of iPhone 4. As we always want to upgrade the displayed technology, such as we are upgrading the iPhone from generation 4 to generation 14 today. Any future upgrade of the retina near-eye display could lead to a more ideal resolution at the dual 16K. At this resolution today, we don't even have a commercial big screen TV to match that resolution. Now, having that many pixels is only half of the equation. We also need to transfer data to display on the dual 8K pictures continuously, ideally at the 60 Hz. Again, if we just calculate the lower end of streaming single 8K video in compressed format, we could need 5 gigabit per second. So this is wider than any typical gigafiber internet service for the household today in the US. So this is a task we will need to put to our communication companies to generate these technologies and services to qualify to create the Retina near-eye display. 5 years ago, when working for a Silicon Valley startup called Lucy, I led a project to create the first prototype 4K dual micro OLED near-eye display. On the left is the design rendering, created working closely with a top industry design firm at the San Francisco. Right out of the bat, you can see that the headset is quite large because there's no way to hide that when you shrink the display to the micro OLED size while maintaining a large field of view, you will need to increase the size of the lens group. There's really no free lunch. But we wanted to hide its large form factor by shaping it like a pillow, which conveyed the perception of familiarity and the feather lightweight. In fact, at that time, the codename of this device was the pillow. On the right, let me play a short video of the CES 2018 show report about the Lucy Alex. As far as I know, Alex is the first 4K micro OLED display to be deployed at a CES demo. And the many news articles after reviewing this demo device has high praise about the beautiful aesthetics of the device.
Now onto a recap of some of the action coming out of this year's Consumer Electronics Show. As Zoe Richards reports, people are still talking about 2 new wearable technologies recently revealed at CES. Here's a look.
At the Consumer Electronics Show in Las Vegas, 2 amazing products were unveiled. The new Lucy Immersion on-demand virtual reality headsets. Lucy Immerse and Alex by Lucy are one of the most ultra HD wearable technology that boasts the most immersive 3D and 4K entertainment experiences available.
Next up, let's take a look at our options for egocentric 3D user input. In this category, there are 3 clear categories: using 3D controllers, using hand tracking, or using full body tracking. Now, for research purposes, of course, we wanted to write papers about hand tracking and full body tracking. But I will be the first to caution our users that if the speed and the low latency is a major concern, then using controllers is still the best option for our users. Now, today, due to the interest of time, we will not spend much time on hand tracking solutions because hand tracking can be considered a mature technology. But overall, we still need to be aware of the 3 approaches for providing hand tracking. First is using depth camera, such as myself created a gesture recognition system for another startup called Athere in 2012. I had about 10 patents contributing to Athere's portfolio. If you wear HoloLens, you will notice that the first generation of HoloLens use camera-based modality to provide hand gesture tracking. Finally, there are dedicated hand gesture sensors produced by various companies, such as the Soli from Google, and there is another very famous sensor solution called the Leap Motion, also designed from the Silicon Valley. But personally, I still prefer the depth cameras because none of the other solutions can support hand gesture to manipulate 3D virtual objects directly from their absolute 3D coordinates. In Berkeley's open source OpenARK library, we also provide a solution for depth-based full body avatar tracking. Next, let me play a demo video. Our former student, Bill Zhou, created this video. In this video, a single Intel RealSense depth camera was used, and the algorithm behind the demo video was beyond the scope of today's topic, and please refer to our open source project for its implementation on the GitHub.
In this demo, we will show a model-based, fully deformable human avatar reconstruction system based on a single RGBD camera beam. This will be available as a module in OpenARK, which will help AR devices better understand the human body and its interactions with other real-world objects. We begin with a linear low-dimensional model of the human body called a symbol. The model consists of joints and shape keys which can adapt to any body type. Given a single RGBD observation, we attempt to fit a parameterized model to the depth image. The model-based tracking allows us to infer missing points.
Gangnam Style. Op, 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 op. Oppan Gangnam Style. Gangnam Style. Op, 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 op. Oppan Gangnam Style. Hey, sexy lady. Op, 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 op. Oppan Gangnam Style. Hey, sexy lady. Op, 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 op. Venus.
As you can see from the demo, the extraction of the 3D simple model from the RealSense depth camera is quite noisy. In fact, that was the main challenge for almost all depth cameras, even more so for earlier generations, such as PrimeSense, acquired by Apple, Softikinetic, acquired by Sony, and the PMD. The average depth air signal could be as much as 10% from the distance of the object. And almost all early generation of the depth cameras also did not work well outdoors. Right now, for consumers and researchers, we have a much better range of advanced depth camera to choose from, such as the Stereolab Z2 camera, Microsoft Asia Kinect camera, and on every iPhone Pro, the current generation, we have a LiDAR camera on the back. There are overall 4 different technologies that will support the manufacture of depth cameras, primarily used for consumer product. Due to the interest of time, I'm not going to go over the pros and cons of these depth cameras. Interested readers can refer to our slides for more detailed in this topic. But I do want to show you in this presentation some visual comparison, emphasizing that different technologies do lead to very drastic differences in the result of the depth. This is a study that's sponsored by one of our industrial sponsors, Ford, to study how to put AR/VR experiences in the future autonomous vehicles. At Berkeley, we have tried to install depth cameras to activate some basic 3D perception functions, such as gesture recognition, face recognition, etc. On the left, I will first play a result returned from an Intel RealSense D435i camera. It used the depth from stereo technology. And the video shows me driving my car in a typical urban environment with the different sunlight and the different vegetation background. And then I'm going to play the same route being captured by the Microsoft Asia Kinect sensor. Now for Microsoft Asia Kinect, it uses the time of flight technology. Hopefully from these 2 videos, you can draw the conclusion yourself about the different depth camera technologies and its effect to the final depth result. The availability of accurate depths is equally critical for room-size 3D hologram applications. In here, I will recommend two demos from Microsoft Holoportation Project and the Google Project Starline. But due to interest of time, I will highly recommend that you can appreciate their proposed technology advancement from their demo videos online. Inferring depth is also important for solving 3D localization, which reveals where you are when you are navigating in the physical world and the virtual world concurrently. In here, I'm going to show you a Pokemon Go AR experience to illustrate the use of 3D localization in a AR experience.
Oh yes! Oh yes! Alex! You got him! Watch out, guys! Hello, heads up! Yeah!
Actually, the initial Pokemon Go to AR experience could only be called a weak AR experience because the 3D localization was solved only using the GPS signal, which gives only a rough XYZ coordinate up to several meters air. For more accurate 3D localization for both XYZ and also the orientation alpha, beta, gamma for 6-degree freedom, up to centimeter accuracy, we have an open source implementation in OpenARK to provide the so-called visual inertial odometry. Next, let me show you a demo video. Imagine somewhere near the origin of the world, we place a virtual cube. This virtual cube can be equivalent to a monster in the Pokemon Go AR experience. And then our researcher is going to walk around and come back to the original space and check on whether the same virtual cube is still at the location initially being placed. And that is the 3D visual inertial odometry demonstration. Of course, visual inertial odometry is not the only way to offer precise 3D localization. There are three primary approaches. The first one is called outside-in, which is similar to localization using GPS satellites. More generally, if you have set up some base stations that can provide periodic signals where you may scan for their timing and strength on your device, then you may infer your own localization based on the technology called triangulation. Oftentimes, triangulation, after an accurate calibration, merely takes the time complexity to search in a lookup table. So therefore, it is very cheap. But it also comes with its baggage that the environment needs to be instrumented, and it does not work if the user walks out of the limited space. The second approach is visual inertial odometry. The best engineering practice will need dual cameras, and an IMU. More importantly, every sensor must be synchronized based on a common clock. This approach is widely used in many all-in-one wearable AR/VR systems and the mobile smartphone to AR experience. The third approach, a recent approach, is called the digital twin localization. In here, we can use camera, IMU, and the LiDAR measurements, but its assumption is different. Digital twin localization will assume our training algorithm can be learned based on a set of known objects and their digital cat models. For inside-out localization, typically it solves both localization and the mapping simultaneously. Hence, there's another name for that called simultaneous localization or and mapping, SLAM. It typically does not use deep learning, but multiple geometry to solve for the rotation parameters R and the translation parameters T, based on the current real-time frame and some stored keyframes in the history. Our OpenARK solution, similar to many state-of-the-art solutions, comes with well-known limitations. First, hardware sync between sensors is a must. If you lost time sync between the sampling stages, it is very difficult to get it back because of the ambiguities of the timing. Second, for SLAM, dual camera setup is always better than a single camera setup. Third, more is not always better. What I mean by that is that some of you may be surprised to learn that many matured SLAM algorithms by design excluded using the depth sensor. Conversely, some depth-first cameras such as Asia Kinect did not come natively with a slant capability, but rely on some third-party implementations. Fourth, less is also not always better. When we don't have depth, SLAM may fail when 3D surface that an RGB camera sees lack visual features. So this is easy to see on the left, that if we started tracking a clear white wall, then we will have no visual features to track. Over time, the localization result will drift away randomly from previous keyframes. More recently, we collaborated with our industrial partners at the Vive Center to work on a different type of localization problem called digital twin localization. We have not released the public code in our OpenARK GitHub yet, but we plan to do so by the end of this year or early next year. But in our experiment, we have seen very encouraging results that we can reduce the 3D localization error to sub-centimeter accuracy. So let me play a demo video from our project team this year.
Hi, this is Team Digital Twin. We're a part of OpenARK project. A digital twin is a virtual copy of a real-world object, system, or process which can simulate the behavior and condition of the represented item. The key problem in digital twin is 6 degrees of freedom post-estimation that identifies the real-world object's rotation and translation. We designed a symmetry-aware post-estimation model that aims for real-time post-estimation tasks with sub-centimeter accuracy, and we achieved 11 frames per second on a 1080 Ti GPU. We visualize our model's performance via a simple augmentation test, where we place a 3D text above a target object. For example, here we set the can as our target object and place a white 3D text object above the target can. We can see that the 3D text moves according to the movement of the camera, but the relative position and rotation between the 3D text and the target object stay almost the same.
Next, let's discuss spatial computing that merges virtual and physical world. For this part, I will largely do a quick highlight to advertise Mohammad's PhD dissertation published this year and draw the selected results from his papers co-authored by me and his advisor Luisa Caldas from the UC Berkeley. And of course, Mohammad is going to discuss all these topics in more detail in his section of the tutorial. The simplest question we may start asking is the problem of asset placement across different platforms. Now, this problem is related to the term responsive display design for websites in Web 2.0. With the websites we are viewing across different platforms from desktop, tablets, and smartphones every day. More specifically, imagine you are a web developer. Before, it is straightforward to write a piece of HTML file to fire up a standard website for PC. But now, you need your website to be properly deployed and viewed across multiple platforms, including with the possible different OS, different smartphones, and any other possible forms in between. These unknown rendering terminals bring challenges to your website design because a website that is not coded to cross platforms cannot be displayed properly on desktop, tablets, or phones at the same time. This is the problem for Java, HTML, and the so-called CSS scripts to solve. However, we also need to recognize that although web designers for 2D need to accommodate different device sizes, resolutions, and their orientation, at the least within the 2D viewing area in a browser app, its UI functionality is uniform. We do not have separate viewing areas for very different interaction and computing purposes. Now, when we carry over the same asset placement problem for 3D AR, our future metaverse developers will face even harder challenges. Namely, when a metaverse experience is being coded, the developer will have no idea what the eventual 3D layout of the spaces such experience will be consumed. Furthermore, if we're talking about consumer applications, our users may immerse in metaverse from very different spaces with the different contextual functions. For example, when we are in a company office, we may have a company layout. When we are in a hospital, we will have a hospital bed and other medical devices. And while when we are in our own home, we could have a living room with a sofa, big TV, and even a fireplace. So clearly, our future metaverse developers will be faced with more challenges to deploy a quality 3D AR experience in one or more unknown spaces. Creating a multi-user AR experience is in fact more challenging than merely managing virtual assets. Our program also needs to manage unknown user input that may be completely out of the control of the program. To borrow the example of website layout problem, although a website layout needs to change with respect to different computing terminals, but at the least, the layout is not affected by the perspective angle of the user and shouldn't change based on different modalities of the interaction method, such as user using a keyboard or user using a 3D controller or the user using a mouse or touch screen. But in 3D AR, because virtual assets are co-located with the physical world and the real users, if unknown user input is not carefully managed, like the example from Mohammad's PhD dissertation highlighted, one person may perceive another user during a virtual interaction by talking into a wall, or perceive another user standing in the middle of their bed. These user placement mistakes will not conform to the expectation of everyday normal user, and oftentimes the scenario will be awkward. To find out our solutions discussed in a list of papers I listed here, please also make sure to check out Mohammad's tutorial session next. Lastly, I want to lightly touch a new issue of privacy we just started thinking about. Earlier, we have seen in Mohammad's wonderful algorithms that calculate the best placement of virtual asset and the best constraint for limiting the interaction of virtual users in physical spaces. But an underlying condition is that we or a company that enable these interaction and the user experiences need to be disclosed about your very private information, about your room and about yourself in order to perform the optimal optimization. This will raise a lot of privacy concerns. For example, it has been shown that if a central entity holds the private information about a user and or their spaces, other users may infer users' own private spaces. Other users may further infer a user's metadata. More dangerous is the case if bad actors get hold of such information, then they may create fraudulent counterparties to scam innocent users. But note that these challenges in safeguarding user privacy is not unique to Metaverse and the Web 3.0. Crimes of fraud or scam are as original as the invention of the telephone or the post office way before the internet, such as we receiving the robocall, or we could receive fake IRS letters asking us for money. The growth of the internet only makes safeguarding user privacy even more challenging. For example, there have been much discussion about how many bot users are infecting social media platforms, such as Twitter or YouTube. For high-profile political topics, you may be surprised or not surprised to learn that there could be as much as 50% of the conversations that have been generated by bots. In AI, it has been well known that DeepMind was famous in training their AlphaStar AI agent by playing against human players and while pretend to disguise their computer agent as another human contender. Much worse is the well-documented deepfake attack, which could hijack the likeness of famous people in order to promote scams online. This will bring to the conclusion of my talk today. We started looking at the Ready Player One as a model of AR/VR technologies, but actually, I think that what the story wanted to tell us is really about how to properly safeguard user privacy and encourage data decentralization. Now, to conclude, let's together will the ending of the movie.
This is wrong. This pen, this contract. This is the moment that Halliday made Morrow sign over his shares in Gregarious. That was the biggest mistake of his life. He knew that. This can't be the end. It's a test. I won't make the same mistake you did.
Oh, good. I just needed to be sure.
This is where you grew up.
Oh, that's just me, a long time ago. I like to have them around from time to time. Hey, I have to show you something. Come on, this is the button. If you push it, the whole simulation shuts down and a tapeworm program will erase all of the backup servers. So you now have the power to turn the Oasis off forever. You understand? Yeah, try not to accidentally erase the whole of the Oasis on your first.
So, how can Metaverse do a better job on privacy? I like what Mark Zuckerberg's view that Metaverse isn't a thing a company builds. It should be the next chapter of the internet overall. What does that mean? It means that compared to Web 1.0 and Web 2.0, in the Metaverse, users themselves should own their own data, and their data should be immutable. When we communicate with the third party, there should be a financial penalty built in that makes the cost of conducting fraud and scam more costly than any potential benefits of the scam themselves, or the so-called trust but verify strategy. Eventually, the entire metaverse ecosystem should be decentralized and not controlled by a single private company. After all, this is what the internet is today, not owned by any single private entity, and the internet is by design interoperable. To open this new chapter at the Vive Center, we have created a Berkeley DeFi research initiative. If you're interested to discuss more about decentralization and interoperability in the metaverse, please check out our website, defi.berkeley.edu, and much of what we are doing within the DeFi initiative is beyond the scope of our talk. But I would like to have a conversation with anyone who may be interested. All right, so this is the end of the first section of today's tutorial. Thank you very much.